Hi students. In this lecture, I am going to discuss problems from HC Verma based on buoyancy force. Let us see first one. Right, see the question. A cube of ice floats partly in water and partly in K oil as shown. Find the ratio of the volume of ice immersed in water to that in oil and given specific gravity for oil and ice. Right? See now how to start. So here condition is ice block is floating. So floating means net force on ice must be equal to zero. That means we can write here force by the liquid must balance weight of the block. Okay. Right. See calculation. Right. First make the given diagram. Right. See what is given here. So ice block. So it is given water and oil. Right. See the block. It is in between. Some part is in water and some part is in oil. So this is water and this is oil. Right, now we have to find out. Suppose oil is up to here, right? And so water is given here. So we have to find ratio of volume of ice immersed in water to that in oil. Let us take side length for the cube is A. Okay, this is now side length. And let us consider X part is in oil, X length is in oil. Then remaining will be A minus X, right? It is A minus X. Now see what we are doing here. So I'm calculating here what is the pressure at the surface and pressure at the bottom. Then pressure difference into area. That gives us upward force. I'm repeating. Writing pressure at the top surface and at the bottom surface. Then taking pressure difference into area. That gives us upward force. And that should balance weight of the ice block. Okay. Let us see now equation for this one. At this point, for example, this depth equal to h. Now see pressure at the top surface. So that will be equal to atmospheric pressure P naught. So pressure at the top surface, that is equal to P naught plus H rho of oil into G. This is now pressure at the top surface. Now focus at the bottom. Pressure at the bottom, that is equal to P naught plus. So I am focusing up to here, okay? Up to here, what is pressure? That means I have to focus H plus X. H plus X into density of oil into G. That is now pressure at this level. Okay. But we want at the bottom surface, okay, at the bottom face. So plus pressure because of water, okay, because of water. That is now A minus X into density of water into G. This is now pressure at the bottom surface. Now pressure difference. Pressure difference means pressure now at the bottom minus at the top into cross section area of the space. That is now A square. It is a cube, right? Therefore, area of the face is A square. This gives us upward force. And this upward force should balance weight of the ice block. So weight of ice block means volume is AQ into density of ice. So volume into density. This gives us mass of ice into G. Right? Now see the calculation part. See what we get PB minus PT. First of all, P naught gets cancelled. See here, P naught gets cancelled. H rho naught G, H rho naught G gets cancelled. See, remaining what else left? These two over. Remaining is X rho naught G, A minus X rho water into G, right? Into A square. Here A square and here one A is left. So rho B minus rho T, that is equal to X rho oil, and even I can cancel G throughout. Okay, here G is there, G also cancel throughout. So X rho naught plus A minus X rho water, that is equal to density of ice. Okay, and see density of ice given how much? Now it is just substituting values, because here we want ratio of the volumes, right? That means here volume in oil, that is equal to A square into X. This is volume in oil, right? And coming to water, it is A minus X. A minus X into A square. That gives volume in water, right? So now simply that means instead of cancelling throughout A square, better we can leave A square like this only, so that this is A cube, here A square, and here also A square. Okay, I am not cancelling. Reason is that we want to calculate now A square into X, that value, and A minus X into A square. Okay, now see what we get here. Substitute values, row of oil. So X into A square, row of oil is, it is given 0.8 plus remaining is now A minus 6 into A square. Density of water we are taking as 1 gram per cc, and this is now 0.9 into A cube. This is equation 1. Okay, next. Let's see here number of unknowns. Here the only unknown, that is X, right? Or if you want to see, if you want to cancel A square here, and if you want to solve for X in terms of A. So from here, we are going to get the value of A. If you want to calculate cancelling A square, from this we get X value, it is A by 2. Okay, so X value A by 2 means half of the volume in oil, remaining half is in water. Okay, So directly we can calculate like this, right? Let us see next problem. Now see the question. Right. A cubical box is to be constructed with iron sheets 1 mm in thickness. What can be the minimum value of the external edge so that the cube does not sink in water? Density of iron given and that of water also given. It is 8,000 and this is 1,000. And given thickness of iron sheets given 1 mm. So condition is that cube does not sink. So cube does not sink means its weight must be balanced by buoyancy force, right? That is the key point. Let us see. So we have to construct now a cubical box with iron sheets. So cubical box, that means we have to consider, see how many plates. We require now 6 plates, right? So we require now 6 plates to construct one cube. So condition is that weight of the cube or that box should be balanced by buoyancy force. It should not sink, right? This is now starting point. And see, coming to weight, this is made up of 6 plates. That means we have to consider weight of each plate. Okay, we have to take weight of each plate. So what is weight of each plate? Let us focus now mass of each plate. Suppose M is mass of each plate. So mass equal to one plate. Area is a square into thickness that gives volume of the plate. See carefully, okay? A square area of the plate into T that gives us volume of the plate into density. Okay, that gives mass of one plate, right? We want weight of the box means weight of 6 plates. So I'm writing here 6 into A square T into rho. That is mass into G. That is equal to coming to buoyancy force. If edge length that is A, right? So A cube gives us volume. Volume into density of water into G. So condition is that it does not sink. In such a case, we are taking our limiting case. That limiting case is, say we are taking, it is just immersed. That means it will be like this. If this is now a liquid surface, it is just inside. Okay. Then see what happens. A square and here A square. Density of water. That is now 1,000 and G gets cancelled. See remaining calculation. So we have to calculate A. So A value 6 into thickness given 1 mm, right? That is 10 power minus 3 meter. Density, it is given 8,000. So 8, 10 power 3, cross check 1, 6. Thickness 1 mm, density 8, 10 power minus 3 upon density of water. And density of water, how much? It is 1,000 kg per meter cube, right? So what else left here? Minus 3 plus 3, or you can say 3 cancelled. This is a 48 10 power minus 3. 48 10 power minus 3 meter, right? Because we have taken density. It is 8,000 kg per meter cube. And density of water also 1,000 kg per meter cube. So answer comes in terms of meter. Okay. If you want to convert into centimeter, this is a 48 10 power minus 3. In the place of meter, 10 power 2 centimeter. Right. So remaining is now 4.8 centimeter. Okay. It is very simple. Key point is that we have to take weight equal to Buoyancy force. And especially you may get confusion while calculating weight of the box. It is weight of 6 plates. Okay. We should not take like it is volume means it is a 4 by 3. Sorry, volume means a cube. Because mass is only mass of plates. Mass is not in the volume. This is simply empty space. Okay. Right. Let us see the next one. Right. So the question given. A cubical block of wood weighing 200 gram has lead piece fastened underneath. Underneath means below. Okay. Find the mass of the lead piece, which will just allow the block to float in water. So again, same condition, floating. Floating means weight must be balanced by buoyancy force. Given specific gravity of wood, that is 0.8, and that of lead 11.3. Okay. So block weight is 200 gram. Let us see the calculation part. So first note down the given data. Weight of the box given, or you can say mass. Mass is given 200 gram. Density say once cubical block 200 gram. Lead piece. Density of wood. Density of wood, that is 0.8 gram per cc. And that of lead. That of lead given 11 gram per cc. Right. Okay. Now see calculation part. So if you make a diagram, so lead is now attached at the bottom. It is at the bottom. And condition is now just submerged. So just submerged means liquid is now like this. This is now dark. Okay. Then see here what we are doing. We are neglecting here volume of this lead piece. Okay. Volume of lead piece. That means how much volume is now inside liquid. It is only volume of that box. Right. Let us see equation. Writing here. Weight is balanced by buoyancy force because floating. So coming to weight, 200 plus it is now mass of light, right? Which we have to calculate into G. So I'm taking directly in CJS only. Coming to buoyancy force, volume inside. Volume inside means it is only volume of the box because we are neglecting volume of this light. Okay. So it is now mass given 200 upon density of wood 0.8. This gives us volume of wood, okay, into density of water 1 gram per cc into G. Okay. So remaining just calculation part. See calculation now. I can cancel G. Now see remaining 200 upon 0.8. So this is equal to see how much? It is equal to 250, right? That means M value. So M equal to 50 gram. So it is very simple and direct. Okay. Let us see next one. Let's see the question given. A cubical metal block of each 12 centimeter floats in mercury with one-fifth of the height inside the mercury. So your condition is one-fifth of the height inside the mercury. Water is poured till surface of the block is just immersed in it. Find the height of water column to be poured. Okay. Given specific gravity of mercury 13.6. Let us see first what is the given data, then how to start it. So first make a diagram. So first of all, it is given one-fifth inside. Suppose this is now mercury. And that object, right? That body is now, it is given like a cubical body. One-fifth is inside. If side length is A, okay, then this is now A by 5. So one-fifth is now inside. And we have learned that volume inside upon total volume, that is equal to density of body upon density of liquid. It is now density of mercury, right? So one-fifth inside means one-fifth of the volume is now inside. So it is now 1 by 5, right? From this we can say density of the body is equal to one-fifth of density of mercury. So this is a condition given to us, okay? Now see what we are doing. We are pouring water now here. So when we are pouring water, what happens is at the bottom, pressure will increase. Okay. When we are pouring water here, because of weight of the water at the bottom, pressure will increase. So what happens is some part of its volume will come out of mercury. That means when we are pouring water, it won't remain one-fifth of the volume. It will be now less than one-fifth. So let me make a diagram for that. Suppose this is mercury. Now, this is that cubical block. And condition is that water is poured up to, it is just immersed, okay? Just immersed. Now here what I'm saying is, this won't be one-fifth, okay? Now that will be reduced. So now we have to calculate how much water we have to pour. Now let us take this as x, which we have to calculate, okay? The length of water column as x. Now see equation. Once again, it is a floating. So it is a floating means. So just as a previous earlier, we have solved pressure at the top and at the bottom, pressure difference into this area. That gives us a upward force, which balances weight of the block. Okay. Writing same equation. Pressure now at the top. That is equal to P naught, pressure of atmosphere. Pressure now at the bottom. That is equal to P naught plus X density of water into G plus remaining C what we get. It is a 12 minus X. Okay. 12 minus X into this is now density of mercury into G. This gives us pressure at the bottom of the tube. Right? Cross check once P naught plus X into density of water into G. Remaining is now 12 minus X into density of mercury into G. Now here what I'm writing is pressure at the bottom minus at the top. Pressure difference into area. That is now upward force, which is balancing weight of the block. Weight is now volume 12 cube into density of body into G. Okay. Now see calculation part. P naught and P naught gets cancelled. This is now remaining one, right? In this remaining G gets cancelled. Okay. So G gets cancelled. See remaining calculation part. What else left? Area 12 square. This is 12 cube. I am writing directly X into density of water, that is 1. I am taking seizures. G cancelled. So it is X into 1 remaining. 12 minus 6 density of mercury. I take that value here directly. Density of mercury. They are given 13.6 specific gravity. So 13.6 gram per cc. That is equal to remaining 12 is left here. 12 into density of body. We got 13.6 upon 5. Okay. What else left? G already cancelled, right? Okay. So here see now calculation part. So I'm calculating here X value. X value means 13.6 into minus 6. And this is X. Remaining is now 12.6 into X. That is equal to 12 into 13.6. This is 12 into 13.6 by 5. So 12 into 13.6 into 1 minus 1 by 5. Right? So remain just a calculation part, right? So from this, we are going to get X value approximately 10.4 centimeter. Okay. So basic condition is that first, from this given condition, 1/5 inside, we got density of body. Next condition, floating. So weight is balanced by buoyancy force. Okay. Let us see the next problem. Let's see the question given. A hollow spherical body of inner and outer radii 6 centimeter and 8 centimeter respectively floats half submerged in water. Find density of material of the sphere. It's a very simple and direct question. Just see calculation part once. Right. Given half of the volume is inside water. Half of the volume. Now see what we can write. Since it is now floating, weight must be balanced by buoyancy. And coming to weight, I am writing volume. You can see mass is only in this volume. Okay. Outer volume minus inner volume. See how much? 4/3 pi outer volume. Given radius is 8. So 8 cube. That is 512 minus 6 cube. 216. Right? 4/3 pi r cube minus r cube. This is volume into density of body into G. That is equal to buoyancy force. Given half of the volume, right? That's why 2/3 pi. We have to focus how much volume. That means we have to focus now outer volume, okay? 2/3 pi r cube. That is a 512. This is a volume inside water into density of water, that is 1, right? Into G. Now see calculation part. Throughout G and G gets cancelled. Pi by 3, pi by 3 gets cancelled. 2 here, 2 times. 2 here, 2 times. And remain just it is density of body, which is equal to 512 upon 2 into 512 minus 216. Okay. So after making calculation, we are going to approximately 865. It is 865 kg per meter cube. Okay. So we are converting into kg per meter cube, right? So it is just matter of calculation. Let us see the next problem. Almost same kind of question we have solved, right? A solid sphere of radius of 5 centimeter floats in water. If a maximum load of 0.1 kg can be put on it without wetting the load, it is now on it. Find specific gravity of the material of the sphere, right? Okay. It is again floating. Okay. So we have right now weight is balanced by buoyancy. So almost same kind of question we have discussed earlier. It is now sphere. We are placing that body on the sphere like this. And if you are taking now condition just without wetting it means it is now like this. It is just inside. This is now limiting condition. So again, writing condition here, volume. So first I'm writing here, weight of both the blocks is balanced by buoyancy force. Weight of both means it is a 4 by 3 pi r cube into density of body into G. That is weight of the sphere plus weight of that body 0.1 into G, right? That is equal to buoyancy force 4 by 3 pi r cube, that is volume, into density of water into G, right? And see calculation part. So G gets cancelled both sides. Okay. And remains what we get here. R value given at 5 centimeter here. Now substitute that value here. Okay. So this value is known. That value minus 0.1. We get 4 by 3 pi r cube into density of body. So directly we can get the value of density of body by making the calculation. And this value comes out to be approximately 0.8 gram per cc. So it is just matter of calculation. I hope you can do calculation.